Time to stop winging it and start engineering it. Welcome to the only podcast that admits the safety factor is basically a prayer. We are mechanical engineering made simple.
Oh, that's painfully true, actually.
Right. I mean, it's the dirty little secret of the industry. But look, imagine for a second that you are sitting at your brand new desk, right? The ink is, it's barely even dry on your promotion to lead engineer.
Oh, boy. The terrifying moment.
Yeah, exactly.
Yeah.
And you suddenly realize, like, wait, if the main structural steel shipment is delayed by even a single week, this entire site just grinds to a total halt. And, well, it's your signature on the line now.
It's a completely different ballgame.
It really is. So today we're taking a deep dive into a mission for a very specific listener. You, the new engineer, taking the reins of your first major project. The training wheels are totally off, and you're the one responsible for managing all this, project uncertainty.
Yeah, and it is a genuinely terrifying transition to make. I mean, you're moving from solving these well-defined, closed-loop textbook problems to navigating the incredibly messy, totally unpredictable reality of actual project management.
Because the variables aren't just neat little numbers anymore, right?
Right, exactly. You can't just plug them into an equation and walk away. In the real world, the consequences of a miscalculation aren't just, a lower grade on a paper. They are blown budgets, missed deadlines, and worst of all, compromised safety.
Which is exactly why, to help you make that leap, we're extracting the most crucial insights from a foundational source today. We're looking at Chapter 2 of Stephen J. Simister's Project Management Guide.
Specifically his work on qualitative and quantitative risk management.
Yes, thank you. And our whole goal here is to equip you to, find those hidden traps before they actually spring. And maybe more importantly, how to somehow explain this massive cloud of uncertainty to a non-technical client.
Without causing a total panic in the boardroom.
Exactly. Without them completely losing their minds.
Well, setting the stage for all of this requires a pretty vital mindset shift, right, from Simister's text. And that is, risk is not something you should inherently fear.
Wait, really? Because I feel like engineers are trained to be terrified of risk.
Oh, absolutely we are. But our industry's relentless desire to deliver projects, cheaper, faster, with more innovative designs that inherently increases a project's risk profile. But risk is actually the engine of progress.
Oh.
Yeah, I mean, without it, there is no opportunity. It's the very presence of risk that allows a complex project to even exist in the first place, to attract investment and actually move forward.
Okay, let's unpack this. Because if you were a new engineer, your default setting for dealing with the unknown is probably just relying on your gut, right?
Oh, 100%.
You feel like you have a sense of what might go wrong based on past internships or junior roles. So you just, promise the client you'll keep your eyes open.
Which is incredibly dangerous.
Right. Relying on intuition for risk is basically it's like trusting a hunch that a custom structural beam will hold without actually running the finite element analysis.
Yeah.
I mean, you might be right, but if you're wrong, the collapse is catastrophic.
Yeah, that is a much better way to look at it than just, hoping for clear skies. When you rely solely on an informal, intuitive approach, you are essentially guaranteeing that you'll be blindsided.
Because you don't have a weather forecast.
Exactly. Unmanaged risk leads to surprises, which lead to forced compromises. Suddenly you're, cutting corners on materials just to meet a deadline. And when those surprises hit, the team defaults to what Simister calls firefighting.
Firefighting, which means everyone is just running around with their hair on fire, right?
Basically, yes. It's totally reactive. You are throwing urgent, usually highly expensive, and honestly ineffective remedial measures at a problem simply because you're in a state of sheer panic.
Gosh, yeah, I've been on sites like that.
Most of us have. But a formal risk management strategy, it pulls you out of that reactive state and puts you in control. Simister outlines this structured, iterative, 5-step process.
Lay it on us.
It's strategy, identification, analysis, response, and control.
Okay, I can already hear the collective groan of engineers everywhere, though.
Yeah.
Doesn't formalizing this process just wrap the whole team up in endless red tape?
Sounds like it would, yeah.
Right, because we want to build things, not sit around a conference table theorizing about every single microscopic way a pipe could leak.
I get that. The hesitation is totally understandable.
Yeah.
But formalizing the process actually does 3 very practical things for you as a lead engineer. First, it provides justifiable decision-making.
Meaning you have data backing you up.
Right. You're assessing known variables objectively, so you aren't just guessing. Second, and this is massive, it creates an ironclad audit trail. Because if something goes wrong later, and let's be honest, things always go wrong on complex builds, You can prove exactly why you made a specific decision based on the data you had at that exact moment. You aren't left holding the bag for a failure you couldn't possibly have foreseen.
Man, that audit trail alone seems worth the price of admission. Like
Yeah.
that literally protects your engineering
It
license.
absolutely does.
Hmm.
And the third benefit is team development. See, in a formal risk workshop, you are taking a snapshot of what might happen in the future.
Okay.
Because the disaster hasn't actually struck yet, the team can explore the consequences of those risks without any fear of penalty or, contractual blame.
Oh, that makes a ton of sense from a psychological perspective.
Yeah.
Like if a junior engineer sees a flaw in a senior manager's timeline during the actual build,
Mm.
they might be terrified to speak up and point it out.
Exactly.
But if it's just a hypothetical workshop, way before ground is even broken, it removes the ego from the equation.
That is exactly the point. It creates this cooperative, no-blame culture where everyone realizes they have to work together to protect the project. But, and the source is very clear on this, the management of risk must not remove the incentive to innovate.
Right, you don't want to paralyze the team.
Exactly. You are managing the uncertainty. You are not trying to smother the creativity that makes the project valuable in the first place.
So we have this mandate to formalize, and we know we need to move away from just, putting out fires constantly. Let's move into the mechanics of step 2, risk identification,
The fun part.
right? How do you actually find the hidden risks? Because you can't just stare at a CAD model all day and wait for a supply chain failure to magically reveal itself to you.
No, you definitely can't. Identification must start as early as possible, ideally during the initial feasibility stage, and it has to continue throughout the entire project lifecycle.
Because new things pop up.
Right. The execution phase itself will generate brand new risks you couldn't have seen on day one. So to find them, you need specific investigative tools. You should be researching neighboring projects or past projects your client has done in the area. And you also need to conduct structured interviews with key stakeholders.
Wait, why structured interviews instead of just, like, getting everyone in a big conference room and having a brainstorming session?
Because group dynamics often suppress critical information.
Oh, like the junior engineer example again?
Exactly. Groupthink takes over, or dominant personalities just steer the entire conversation. Sitting down with someone one-on-one pulls out a much greater depth of insight. They will tell you the ugly truths about a specific contractor or a design flaw that they would never ever say out loud in front of the client.
That makes total sense.
Ah.
Now, the source also mentions using checklists, specifically looking at variation orders from past projects. And a variation order is basically documented proof of an unmanaged risk from a previous job, right?
Yes, essentially.
It's almost like reading the autopsy report of a past failure to prevent it from happening on your current project.
That is a brilliant way to frame it, an autopsy report. But the most critical conceptual tool for a new engineer to grasp in this phase is the differentiation between 3 distinct elements: cause, risk, and effect.
Cause, risk, and effect.
Yeah, you have to map these background conditions accurately, or honestly, everything else just falls apart.
Okay, let's walk through that map. How do those 3 actually differ in a real-world scenario?
Sure. So the cause is the background condition. It's a factual given about your project. For example, your project is located in a specific, rapidly booming city.
Okay, booming city, got it.
Right. Then the risk is the area of uncertainty driven by that cause. In this case, because the city is booming and construction is everywhere, there may not be enough suitably qualified labor available locally.
Makes sense.
Finally, the effect is the consequence. If the risk actually occurs, you have to bring in outside labor from another state, which significantly adds cost and time to your project.
Okay, so treating the effect is kind of like putting buckets under a leaky roof, right?
Yeah, exactly.
But managing the risk is finding the actual structural flaw in the trusses that's causing the roof to sag in the first place. But here's my pushback. Isn't it just human nature to try and fix the effect? If you need labor, you just buy it. Why does treating the effect completely blow up an engineer's budget?
What's fascinating here is that if you only manage the effect, you are expending all of your financial and mental resources on the consequence rather than addressing the root uncertainty.
So you're just buying more buckets.
Exactly, you're buying buckets. If you just throw money at outside labor, you haven't addressed the secondary risks, like what if the imported workers aren't suitably qualified either? What if housing them causes this massive logistical nightmare?
Oh, wow. Yeah, I didn't think of that.
Right. But when you map the cause, risk, and effect in a structured workshop, it encourages lateral thinking. The team begins to see interrelationships.
Hmm.
You might manage the actual risk by altering the engineering design to require less specialized labor, like utilizing prefabricated components rather than just accepting the effect and paying a premium for imported workers.
Wow, that completely changes the approach. You are essentially engineering the risk out of the design rather than just bracing for impact.
Exactly.
Okay, so we've mapped the root causes, we've isolated the specific risks. But look, if a new engineer walks into a client meeting with a spreadsheet of 50 potential disasters, that client is going to absolutely panic.
Hmm.
How do we filter out the noise and figure out which of these actually matter?
That brings us to the third step, risk analysis. This translates all that raw data into actionable intelligence, and it's done in two phases. First is qualitative analysis.
Okay.
This is where you use a probability and impact matrix. You are scoring the likelihood of a risk occurring against its potential impact on, say, cost or time.
So essentially, you're building a visual heat map.
Yes, but to make it work, you have to define the scales objectively. You can't just say, oh, this has a high impact.
Because high impact means different things to different people.
Right. You have to define that a high impact risk means the project cost increases by, let's say, more than 50%. You plot every identified risk on this matrix. The risks that land in the high probability, high impact corner, those require detailed review and active management.
And the others.
The ones in the low probability, low impact corner, they might just need a basic contingency plan. It visually filters out the noise.
Okay, so we do the heat map, and we know our priorities.
Yeah.
But eventually, I do have to sit down with the client and ask for a contingency budget to cover the big stuff. Do I just, slide the heat map across the boardroom table and ask for a blank check?
Absolutely not. Do not do that. That is where qualitative analysis ends and quantitative analysis begins. Quantitative analysis applies actual statistical modeling to your risk. And before we even get to the complex simulations, the source highlights a simpler visual tool, decision trees.
Decision trees. Like a flowchart for bad choices.
Essentially, yes. Decision trees help you visualize the expected outturn costs of distinct branching choices.
Give me an example.
Let's say you have a specialized contractor who is falling way behind. You have two choices. Stick with them and risk a massive schedule delay, or fire them and pay a massive premium to bring in a new contractor at the last minute.
The classic rock in a hard place.
Exactly. A decision tree calculates the probability of success for each branch, multiplied by the cost. It mathematically proves to the client whether sticking with the bad contractor or eating the cost of a new one is the statistically cheaper option.
That is incredibly practical. But what about the overall project budget? Because the decision tree works for one contractor, but a massive project has, thousands of variables?
Yes, thousands. For the entire project, you use a Monte Carlo simulation.
Okay, I've heard of this.
Instead of just saying a delay might happen, the Monte Carlo software assigns a probability range to every single variable. Concrete curing time, steel delivery delays, labor shortages, everything. It then runs thousands of random scenarios to see how all those variables interact with each other.
That's intense.
It is. And the output is a probability distribution, which is usually displayed as an S-curve graph.
Okay, so I have this S-curve graph showing thousands of random scenarios. How do I actually use a Monte Carlo simulation to, ask the client for real money?
Well, the simulation gives you exact data points. Let's say you run the model, and it shows that at a 50% probability level, your project will cost $229,970.
Okay, $229K.
Right. This means half the time the simulation ran, the cost was at or below that number. But no engineer wants to operate on a coin flip, right?
Right, 50-50 are terrible odds for a bridge.
Exactly. If you want a more robust safety margin, you look at the 60% probability level on that exact same S-curve. And at 60%, let's say the cost is $249,180.
Here's where it gets really interesting. Because you don't just walk in and ask for 250 grand, do you?
Yep.
You subtract the baseline from the confidence level. You take the 249,000 for the 60% certainty, subtract the 229,000 baseline, and you get exactly $19,210.
Yes.
So you don't just walk into the client's office and vaguely ask for 20 grand just in case.
Yeah.
You put the S-curve on the table and say, to achieve a 60% certainty of project success, the statistical model requires a specific risk allowance of $19,210.
Yes. And notice how that completely transforms the conversation. You are educating the client. You're moving them away from the dangerous illusion of a single point estimate.
Because clients always want to fixate on one rigid number.
Yeah, always. By providing a realistic range of parameters, you mathematically justify your contingency budget.
It totally changes you from, a nervous junior employee asking for a favor into a data-driven professional providing an engineering solution. That's huge. Can you do this for the timeline too?
You can, using criticality indexes. This shows the client exactly what percentage of the time a specific activity falls on the critical path during the simulation.
Okay, let me stop you there for the listeners who might be entirely new to project management terms. What exactly is a critical path?
Good question. The critical path is the longest sequence of dependent tasks that dictate the project's absolute minimum timeline. If an activity is on the critical path, any delay to that specific task inherently delays the entire project.
Oh, okay.
For example, painting the interior is usually not on the critical path. You can do it whenever, but pouring the foundation is. A criticality index tells you how often a wildcard task suddenly becomes a critical path task due to other random delays in the model.
That is incredibly powerful data. But there has to be a catch. I mean, we're relying entirely on a computer model here.
And that is the danger. Quantitative data is incredibly powerful for clients, but it is completely reliant on the G.I. Joe principle, garbage in, garbage out.
Right.
The Monte Carlo simulation is only as good as the underlying data you feed into it. If you rush the qualitative stage, if you skip those structured interviews, if you fail to accurately map the background causes to the actual risks, your beautiful S-curve is just a mathematically precise lie.
Oof. A mathematically precise lie. That is a terrifying thought for a lead engineer.
It should be.
Okay, so let's say we've identified the risks properly, we've modeled them without lying to ourselves, and the client was so impressed by your S-curve that they approved the budget.
Right.
But now you actually have to execute step 4, the risk response. So I've got this fully funded, mathematically precise plan. Do I just buy a massive insurance policy to cover all the risks, or is there a way to actually engineer them out of the project?
Well, you have multiple levers you can pull here. Your responses will generally fall into one of 4 categories. First, avoid.
Avoid.
Right. You change the project plan to entirely sidestep the risk, like altering the design to remove a hazardous material. Second, transfer. You shift the financial burden of the risk to another party, usually through insurances, performance bonds, or specific subcontractor agreements.
Okay, pass the buck.
Exactly. Third, mitigate. You take active steps to lower the probability or the impact, like ordering materials early. And fourth, control. You accept the risk, but monitor it closely.
But the source has a massive warning label attached to these responses, doesn't it?
Yeah.
Specifically regarding secondary risks.
Yes, and this is where so many new engineers get tripped up. The golden rule is this: you must evaluate the original risk with your response in place, which we call the reduced risk, and add any new secondary risk that your response created.
Wait, run that by me again.
If the reduced risk plus the secondary risk is greater than the original risk alone, your response is terrible. You have made the project more dangerous.
Okay, let's apply that to the steel shipment example from the very beginning of the deep dive. The original risk is that the high-end structural steel from overseas might be delayed by shipping issues, threatening the whole timeline.
Right. So let's say your response is to avoid that timeline risk by switching to a cheaper, locally sourced steel. Your shipping risk is now 0.
Problem solved.
Not quite. Because that local steel introduces a secondary risk, it might contain microfractures that fail to meet the load-bearing requirements, potentially causing a structural failure.
Oh, wow.
The catastrophic impact of that secondary risk far outweighs the original shipping delay. The response failed the golden rule, and you need a new plan.
You cannot let the cure be worse than the disease. That makes so much sense. Which brings us to the final piece of the puzzle, risk control.
Yes.
The source says the absolute nerve center of this entire operation is the risk register, which is usually just a massive spreadsheet logging risk numbers, probability factors, impact scores, all that.
Yeah.
But here is my question for you, representing every single engineer listening. Why do we always abandon these things?
Yeah, it's so common.
We fill out this beautiful, complex risk register on day one, and then we just shove it in a virtual drawer to gather dust while we go deal with the actual construction site.
Right.
What is the mechanism causing that failure?
The mechanism of failure is entirely psychological. Engineers frequently view the risk register as a compliance document.
Box to check.
Exactly. They think it is just a piece of paper generated to satisfy the client or the regulators, and once it is signed and filed away, its job is done.
When in reality, it should be the dashboard for driving the project.
Precisely. If we connect this to the bigger picture, risk management is an active, continuous pulse check on your project. To keep the risk register out of that virtual drawer, You must shift your mentality and use it as your primary management tool. You have to religiously update the status column every single week. Every single risk needs to be tagged as done, active, or monitor.
Walk me through those tags real quick.
Sure. Done means the risk event passed and was dealt with. Active means it is currently being managed and resources are actively being spent on it. Monitor means no response is required yet, but it is on the radar.
Got it.
Furthermore, unless you assign explicit ownership to each risk, naming a specific person responsible for the management action, the whole process fails through bystander apathy.
Everyone assumes someone else is watching it.
Exactly. Risks change constantly with time and inaction. Constant control is what keeps the system alive.
So what does this all mean? It means that as a new engineer stepping into the lead role, you have to completely upgrade your operating system.
Okay.
You are leaving behind intuitive guesswork and adopting a formalized engineered strategy. By mapping the true background causes to the actual risks, you stop wasting time and money treating the symptoms. And by utilizing tools like decision trees and Monte Carlo S-curves, you can confidently walk into a client meeting and secure the budget you actually need based on hard statistical data. You are building a living, breathing system that tracks, mitigates, and controls uncertainty from day one until the final handover.
That sums it up perfectly. And as we wrap up this deep dive, I want to leave you with one final profound detail from the source text that speaks directly to your role as a leader.
Lay it on us.
Simister clearly states that complete transfer of risk is rarely wholly effective or indeed possible.
Wait, really?
Yeah, you can buy all the insurance in the world, you can write rock-solid contracts, and you can subcontract out the most dangerous tasks. But ultimately, if the project fails, the reality of that failure will always bounce back to the primary stakeholders.
So you cannot just paper your way out of responsibility.
Exactly. So as you step into your first major project, I want you to ponder this. If you can never truly transfer 100% of the risk away from yourself, how does that fundamentally change the way you define your professional responsibility as the lead engineer? If the safety factor really is just a prayer without a solid risk management plan backing it up, what are you going to do tomorrow to ensure you aren't just winging it?